So yeah, the next speaker is Jonathan Sprinkle from, wait, what happened? Oh yeah, from Arizona University or University of Arizona, I don't know which way. And the title of the talk is Challenges in Set-Valued Model Predictive Control. Please.
Fantastic, and thanks for the introduction there. I'm going to take a little bit of a different tack in the workshop presentation. I've really enjoyed the technical talks and a lot of the results that we've seen earlier, and there will be some opportunities to perhaps draw some parallels between some of the work that's really grown out of some efforts by Natalie Burke and Ricardo over the last couple of years. But where I'm hoping that we'll kind of end this portion of the session is with some opportunities for discussion and maybe some people to ask questions about what the future for this might be and different regions in which we might go. Because we have had some really great technical results in this area, but really this talk is kind of about the challenges that are there to bridge that theory to real gap in being able to apply some of these results. And so hopefully that's what we'll take out of it today, and we'll have some great opportunities for questions in a couple of minutes. I think, one thing that was really clear in the previous talk from Stan was this idea of using MPC for controlling vehicles that got to keep moving. This is something that's kind of near and dear to my heart from my introduction to model predictive control back in 2003 or 2004, where we were working on pursuit evasion games between fixed wing aircraft. And really a big portion of that had to do with making sure that we don't violate constraints like whether or not the vehicle still has lift, or whether we're going to fly out of a zone that would be inappropriate for us to fly in. It would be a no-fly zone of some kind. So those pursuit evasion games started with some of those dynamics that were different from the Dubin's car and different from some of the previous results that were used on rotorcraft, where with rotorcraft, it was somewhat straightforward to just stop and turn and then move away, whereas with a fixed wing aircraft, you have to keep moving and you have a different turn radius at different speeds. And so there's all these dynamically inspired trajectories that you can fly. Alongside of that was some work done about 5 years ago now with Quinn Zhang. So I think I'll play both of these videos at the same time. The one in the middle here is showing the use of MPC moving through an obstacle field, where that obstacle field has to do with ensuring that we don't violate the corners or the circles that are there. But we want to go as fast as we can. And so as we're driving and moving fast, we might switch between two different predictive models that our model predictive controller would be using. And in doing so, and you can see kind of the color gradation there, moving back and forth between whether we're pink or whether we're black. That's telling the predictive model that we're using based on that vehicle's dynamics. And it has to do with how fast we're going. So if we're going faster, we use a different model because the dynamics are not so different from that model, and we don't have to worry as much about model error. And the results of that were showed by two fantastic students that were part of an undergraduate program here. I'm going to just back it up a little bit so you can see a little bit more of the kind of work that these students were doing. So they were going from these were two undergraduates. They were part of a summer research program, and they were driving this car in the parking lot to try to validate some of the theory that Quinn had done. And so in doing so, the movie is sped up there. I don't want you to think we let our students drive the vehicle that fast. But a lot of the ideas were the same, that we have this box and we need to move the box in between these circles and make those circles not be penetrated in some way by the box itself. So all of those previous work for MPC had some tremendous benefit in being able to, I think now I have to figure out how to get past this slide, to advance the state of the art in this idea of canonical MPC for car-like robots, where we want to follow some kind of trajectory and we want to have us not hit some kind of an obstacle. And if you look at kind of the basic formalisms of that, we've heard a few examples of it earlier today. That we have some state update dynamics where we get the next state based on the control input and based on the state prediction. And then we also have a state prediction that may or may not be what the actual dynamics of the system are. So we approximate it maybe with some tilde to say that tilde might be the real dynamics or either the approximate or real dynamics. But what we've got as our predictive model is this G of XU. And we use that G of XU to predict our state over some horizon J. And we build a cost function with the terminal value as well as all the different aspects of whether we might be violating constraints or going too fast or getting away from where we want to go to. All of those things are baked into the cost function. And at the end of the day, the idea is to minimize the cost function as best as you can by selecting the best kind of inputs that you have. So baked into this is this idea that I know what is good. I know where I need to be. And I know how far away I am from that kind of at any given time. And these are all valid for the kinds of systems that are following a specific trajectory. So I want to instead think of an idea, and that's really what's motivating this idea of set value dynamics and set value MPC. I want to consider again that I'm in a box, but that box itself, not a trajectory that's the middle of the box, but that the box itself is moving in the future. And we're predicting the shape of that box. And we have some dynamics to describe the set itself. So this is a little bit different from other kinds of approaches that might be thinking about uncertainty. Certainly you can consider uncertainty in this way, but it's different from, say, a tube-based approach where I know that I'm going to be somewhere in this region based on uncertainty that I have in the model, but I'm not sure exactly where. So this idea of a reachable set is a very similar kind of idea that you factor into it all of the inputs that you might possibly give, and it's going to give you all the outputs that you might possibly see. So the reachable set idea is one that I think is well known, that's very difficult to compute in real time unless you do a tremendous amount of over approximation. And then your safest move might be to not move at all, because your operations had to be so conservative to ensure that you didn't collide with anything, which was a kind of an old joke that we had from the DARPA Urban Challenge when we started fielding some controllers that were safe controllers, and the safest controller was just to take the key out of the car and just walk away. So we want to think about these set value dynamics, not just the trajectory synthesis idea, but the idea of having the dynamics of the set, so that's this X positive, is valued by some dynamics that are themselves based on sets. So in this case, X is a set, it's the lower left-hand corner here, and the evolution of that set to the next time step comes from X plus. And U, again, might be a set of potential inputs, and those set of potential inputs will give you this set of potential outputs in the next time step. So with some math that I think you might really enjoy reading from some of the earlier papers that I have linked on, you can dive a little deeper into the various maps that we have and the rules that come about whether the sets are closed or not, et cetera. But it's very analogous to this idea of, you know, Rn cross Rm, except now we're thinking about the power sets of all of those ideas when we're making the map from one to the other. And again, this is a little bit different from thinking of point to point that's validating a specific trajectory that you have. So if I want to get from X to X positive, I enter my value U. U is probably a predictable value. There's probably not some stochasticity in a model that we might be using. So we know exactly where we would predict that we would be. And if our prediction doesn't maximize our cost function, we choose a different control input, or minimize our cost function. We choose a different control input to get the value that we'd like to have there. So with that in mind, there's a couple of challenges that come up to this that may or may not already have been clear when you were looking at some of those pictures. The first, what should we use to measure the distance or the error of one cost of one prediction into the future compared to another? So what kind of analogs can we use between this idea of whether my trajectory seems to be minimal and provide the lowest cost possible, if we're instead considering the set of the initial conditions based on the set of inputs that we might have? And if we have about an idea to do that distance and error, then what kind of set value model predictive control properties can we derive or can we validate? And do we need to make some kinds of assumptions on that would make the theory itself really not work? And then finally, what approaches can we use to build set dynamical models that might be data informed for cyber physical system deployment? And again, one of the reasons that we're thinking about these set valued maps, besides the fact that they're intellectually very fascinating, is that we'd like to be able to think about how to have more runtime guarantees to be done, that we know that we're going to get behavior that we're happy with because we're simulating the entire set of behaviors at runtime when we're predicting what might happen. And we're ruling out values that are going to violate our constraints. So if we were able to do this, and germane to the topic of this workshop, we're not exactly sure what those computational demands might be at this time. It might be completely infeasible to do, or it might be feasible to do by computing at the boundaries. We're really not sure. And so that's part of the means for moving forward with the discussion. So again, just kind of putting this into a visual framework, we have an idea of the distance and error that you might see for predictive control for a specific trajectory. In this case, maybe our first iteration on the cost function with the guesses that we think we would have based on our predictor function, g of xu, will give us some points here that aren't exactly on the best trajectory. And so we would do an iteration to maybe get points that would be a little bit better for the future iterations. And we're doing that based on measuring that cost itself, based on the function, the cost function j of xu. So thinking about this in terms of the challenges that would come from set dynamical systems, we have maybe this is a great trajectory, or maybe this is a better trajectory. Just looking at these things, obviously it's a little harder to figure out which one might be better than the other. And so we turn to some existing theory from math to get an idea, or existing applications from applied math to get some ideas about what we'd like to consider as the measurement functions and the metric spaces. So an example of this is using the Hausdorff distance as the chief metric for measuring the distance between two sets. So if we want to minimize the Hausdorff distance, it's going to result in a minimization of a maximization of the minimum distances between the two sets, or a minimization of the maximum distances between the two sets, depending on the areas that you're looking at. This is something that really is, to be able to define it in this way seems a little bit more complicated than it has to be, but it actually kind of has to be this way. So we're looking for the biggest distance between set A1 to the closest point in A2 across the entire set. So if we can minimize these two values, it's more likely that these two sets would be the same set, or they would at least overlap in a significant way. And so being able to measure this kind of cost difference between allows us to judge whether one set is going to be better than another set, or whether it might be diverging from that set in some of the regions, which would result in things that we basically wouldn't like to see in a predictive control application. And so some examples for these of how we've been able to think of these set dynamics with respect to physical systems are from a paper that Natalie submitted to CDC just a few weeks ago. And so I've produced a few of her images here in order to try to ground this. So if we look at set dynamics with the boundaries that we have for the vehicle itself and the projection into the future based on that, in this case, we're starting with an initial set x0, which is in the space q1 and q2. And based on that initial set with a single input u, so u is not a giant set, it's just a singleton trajectory, then we can project the set-based dynamics essentially just by moving the entire set through the dynamics that we would expect from a specific controller u. And we see these boxes kind of moving throughout to tell us that at various times, x0, x1, x2, we continue to move, and we can project that idea into the future. So using some of the existing computational tools, it's somewhat straightforward if you have only one of the elements of the system be a set, and you're not concerned about all of the elements each being sets. That's when it becomes a little bit hairier to look at. So thinking then about a set value dynamics that's not just with a certain input u, but with u as a function that's coming out of g of x. Now you're actually thinking a little bit about how I might make this box move into a certain final condition. So this is really looking at the forward reachability or backward reachability, depending on how you're projecting it. And so in this case, we've defined the set in terms of a new state space. So we've defined x in terms of its, the initial conditions between point 1 and point 2. And then the initial conditions in y between point 1 and point 2. But now we're having some dynamics for all the edges of the set that are based on the input values. So this is, again, a slightly different take on how we're thinking about how the set itself evolves. But the values for U1 and U2 are based on measuring the error of the set over time. And so as that set error is propagated into the future, then we're using the feedback from that in order to choose new values for U1 and U2 in order to meet the metrics that we have. So the analog of this is if I'd like to park this car in a parking space, and I'd like to not hit any other cars as I go into that parking space, then we would have a cost function that would define those other regions where we never want to intersect with anything in those regions. And we'd like to put the car in as few moves as possible or as little time as possible into the final location. So some of the properties that we're currently looking at and that might feature a little bit in some of the discussion later is to think about the kinds of conditions for set valued MPC that we know to a large extent for existing MPC systems. So will our system be stable? Can we show that there will be some kind of invariance from a certain point that will always arrive at a point later, or that will stay within a set once we enter the outer region of that set? Again, as I pointed out earlier on, we're interested in figuring out what's the computational cost of solving for these trajectories based on the sets that we have and the initial conditions we may begin with, or the complexity of the dynamics that go along with what we're continuing or what we're attempting to control for. And then if we can approximate the set value trajectories, that would enable us to do faster computing, and that might allow us to associate some accuracy or inaccuracy with some of those changes that we might have for the potential dynamics that we would be using. And this is something, again, that's explored pretty heavily within the MPC literature to think about whether there's drawbacks to approximating your function, whether you should actually use the control input that returned from your MPC solution, or whether you should have that synthesize a trajectory and you use a separate controller to just follow that trajectory. So there's lots of other meat on the bones here in terms of exploring where this kind of system would go. Where I want to move next into the presentation is to look at how we might consider the relevance of these kinds of things with data-informed models. And this is in the context of some ongoing work that we've been examining data from naturalistic drives over about the last year. We have something now like 20,000 plus kilometers worth of data, but a subset of those data are relevant to this particular task because they're from vehicles that we can measure other kinds of things in. So we get better data from some aspects of the vehicles. And if you saw Vishnu's talk in the kickoff earlier today, he was talking about some of the fantastic features that exist in today's vehicles that have come out of the kinds of labs like TRI and some of the fielding that's been done by Toyota Research in general. We're taking advantage and leveraging a lot of those kinds of things by plugging into the CAN bus of the vehicle, being able to access radar data, wheel speed data, et cetera, with really low cost, and get it in very naturalistic situations. So what we're interested in is looking at drives like this one, where the car may or may not be going straight, it may or may not be turning. And so we're looking at very specific kinds of inputs over a range of inputs to get an idea for how the vehicle's dynamics might be the same or might be different based on a set of inputs that are very similar but not identical over time. So this is going to give us a way to think about how we might have concepts such as set value dynamics, system identification moving forward. So where I've done a significant amount of sort of downsampling of the kind of data that we have so that we can present it here is to look at selected data from a single kind of vehicle. So these are all data from a Toyota RAV4, and they're all data from stop. Means that we have been stopped within the last little bit. We were stopped for at least 1 second. And then moving forward, we moved for 3 seconds. So obviously we have no idea what might happen 20 seconds from now, but for the next 3 seconds, I'm interested in knowing how might the vehicle react based on the kinds of inputs that were provided. And the kind of inputs that you can give to a car-like robot are acceleration angle and yaw rate or steering rate, however you want to think of it, as the output from there. So based on these two values in the acceleration, you can project based on the kinematic model of a car-like robot to predict where the car might be at those times within some kind of error. And so looking at these points here are about 2 days worth of driving. So, probably the maximum distance that we had even before we downsampled all of this was in the neighborhood of like 100 kilometers or so, probably less. But it features a significant amount of information even just from that. So looking kind of within the same scope that we saw earlier of an initial condition in a box and then some other boxes that came after that, I've been able to project the data into that exact kind of framework, looking at different ranges of output speed, which are therefore constraining different ranges of inputs. So the output speed, for example, after 3 seconds from a stop, in this case, it's all the output speeds that were between 15 and 20 kilometers per hour. And then you can see a pretty tight correlation of the values of the accelerator that would give you 15 or 20 kilometers per hour. We don't see a really broad range of inputs here. And in fact, we don't see that drivers themselves do a lot of turning if they're doing 15 to 20 kilometers per hour after 3 seconds. Mostly at this time, if you're speeding up that fast after a stop, you're pretty much going straight. In the example of between 10 to 15 miles per hour, we see a slightly larger spread in the accelerator versus time. And again, some different kinds of behaviors in the yaw rate versus time here. And as we speed down, so this is between, I think, 5 to 10 kilometers per hour. There's a typo on the title of the slide. In this case, we're seeing that there's a lot of turns. And in fact, for this one, most of those turns are to the right. And then for the final one, we have some turns that are both to the left and to the right. And in this case, we see lots of different examples of yaw rate, but not a lot of different examples on the accelerator. So we have a lot of different speed outputs, but generally, if you're doing this, you're probably doing it on idle. You're not actually pressing the accelerator to do something. So looking at these in the Q1, Q2 space, just like we had before in the car-like robot example of the Dubin's path, we can see lots of really interesting things with just a little bit of valuation here. So the first is that if you're moving at low speeds, strangely, there's a much larger uncertainty as a percentage of how far you've moved here, because we're not sure exactly what we're doing, and there's a lot of different kind of behaviors that happen at low speeds. But if you think about some of the larger speed cases, you can see that even though the pictures might be a little bit faint here for the outlines of the lines, but each of these blue lines here is capturing the containment space of all the positions at that particular point in time. And so in this case, I think I'm segmenting them every half a second or maybe every 0.2 of a second in order to get a bound at that particular time for where the vehicle happens to be. And so by looking at all these values, we can also begin to infer that the dynamics that we may be seeing in these different kinds of regions are not actually going to be as big as we might think. It's not going to be the entire Dubin's curve for any particular kind of input that you might have from a stop. If you know a little bit about the input space in terms of either the velocity or the yaw rate, you might be able to predict what the output space is going to be a little bit better, which is going to provide you with perhaps some tools on being able to make approximations of the set dynamics based on other kinds of inputs that you see, and to rule out some kinds of dynamics that you definitely would not be seeing based on these kinds of naturalistic driving. So I'm hoping that we'll have, again, some time at the end here to have some great questions, but really what we're interested in is looking at more of these kinds of properties that can be shown for the convergence of set valued MPC. There's a lot of really interesting theoretical work that might be able to happen here that might inform the kinds of data that we would need to get so that we could build data-informed models. And then we can start to think about the computational burden of the controllers and the kinds of benefits that it would have in order to field these controllers on either low-cost devices that would be used for research in order to prototype, or perhaps to have them encoded on ECUs and living inside of a car to be thinking about the kinds of outputs that you might be seeing in adaptive cruise control or cooperative adaptive cruise control, so that we can start to field more kinds of applications that would benefit drivers in terms of safety. So I've also included here a couple of links to the DOIs for particular interesting papers that might provide a little bit more context, but I'll defer maybe also to some of my co-authors on some of the efforts that you may have specific questions on. I do want to say a special thank you to the support from the National Science Foundation and to the Department of Energy. And thanks to Rahul Badani, who wrote the stream package that we're using in order to do a lot of the data processing that we have going on. So I think with that, maybe we'll have a few extra minutes for discussion here. And thank you for your attention.
Thank you. So is there any question for Jonathan? I have some question, but let's see. So yeah, maybe I start with my own question. So this set valued dynamics, was it equality or inclusion? Was it set valued inclusion or set valued equations? The dynamic, the formulation you wrote in the beginning. Oh wait, you are muted. Yeah. I
was muted. Curses. These are equalities here, but I'll defer to Ricardo if there was a slightly different approach that this might be approximating for some reason for simulation.
Yeah, the general framework is with equation but I mean, turn it into an inclusion is, is a possibility as well.
Yeah, but I mean, what I was wondering is, isn't it hard to come up with equality? Because that means you're computing exact reachable set. That seems very tough to do, yeah?
Right, from an analysis viewpoint, from the theoretical viewpoint, essentially what this does is a propagation of sets, right?
Yeah.
And the beauty, to some extent, of equality is that then the solution that you have forward in time from propagating a set is unique, right, under certain conditions. If you throw in inclusions, like the next state belongs to a set, then it becomes a little harder. You need to assume that you are picking probably the right type of sets from the right-hand side. But I totally agree that it's almost like defining the reachable set from a dynamical system in a theoretical manner. We are not yet worrying about how to compute it at that stage, but just defining it. When it comes to approximating it, that's definitely challenging, regardless of whether it's equality, inclusion, set dynamics, single value dynamics, or whatnot.
I mean, I would have, so for example, if you allow inclusion, so one way of computing this dynamic is, I don't know if Murat or Sam are here, they have this, for mixed monotone system, they define this function f, and that function gives them the corners of the hyperrectangle containing the exact reachable set. And in fact, it touched the reachable set in a tight way. So if I use that function, I can come up with the set valued evolution, but in an inclusion way, yeah. But I don't know if that's going to be helpful for, I don't know, if you want to ensure safety or something.
Right, and that's exactly what we're doing, Majid. We are, the set you might start from, right? The initial set here, x sub 0, you can pick it as you want, right? And then maybe under some convexity or some structure of the set, the propagation of that set amounts to just propagating a finite number of points, right? For the linear case, that works quite well. And in that case, you would be, essentially by writing a set dynamical model, what you would be doing would be to approximating the behavior of a non-set dynamical model, right? With some essentially bounds on the disturbance, which are defining the set itself. So for computational purposes, where we are at is the level 0 to some extent. So we are working with polyhedrals that via linear transformations retain their structure, right? And the set itself that we are propagating is an approximation of some essentially probability distribution of where the state might be, right? And more general constructions would require more complicated analysis. But at the end of the day, what you do when you propagate the vertices of these squares, right, or rectangles, is you're having an equation, you don't have an inclusion right there.
But convexity may not be preserved, yeah? If you only simulate the edges, so you may become concave if it's nonlinear, so.
Right, there are some properties that we can discuss where you can preserve, let's say, rectangles will preserve rectangles, right? Or polyhedrals will preserve polyhedral shapes. There is quite a bit of work in that domain, which we are learning as we go. But what Jonathan was saying is that our MPC, as a difference, perhaps some people might have this question, as a difference to tube MPC, what we are doing is optimizing over the entire set rather than optimizing relative to the centroid or a particular point in the set. And that allows to design controllers, at least from a theoretical standpoint, that can be done. So we submitted some work to the CDC. It's our first step in that direction to synthesis. But the question is then, how do you deal with the computing effort required here, right? So let's say you want to solve MPC over a set. That means that you need to essentially formulate an optimization problem over sets over a finite horizon, right? And as you know better than me, probably you need to maybe abstract that set somehow. So maybe discretize or parameterize or the such, and that's where we will use quite a bit of help. I think some of the questions that Jonathan has at the end of the presentation, do you still have them, Jonathan? Those would probably bring some good points to the discussion. I think hopefully that answers your question. But yeah, so that's the first question is what computational tools can be useful to do this efficiently. And we can argue about equality or inclusion, but I think the point is there that how do we compute this efficiently? And one of the references that Jonathan mentioned, we ran some experiments on obstacle avoidance for a quadrotor where we were essentially propagating the sets based on estimates of uncertainty, and we were able to solve it with a very simple OptiTrack MATLAB, ad hoc closed loop via the mockup, the problem in real time. So the question is, how do we do this? Verify and extend.
Yeah, I mean, yeah, I guess also some properties on the dynamic can also be useful for computing this set-based MPC. Like monotonicity or mixed monotonicity, I assume they can be very handy in this case. Thank you. So is there any more question?
I had a quick question, Jonathan, if you don't mind. You talked about looking more at the computational aspect and how it's going to impact. Can you speak a little bit more into the direction of what type of techniques you want to look at to solve this and how that might impact computation?
Mm-hmm. Yeah, that's a great point that it may be that as we start to look at this, it's going to be really computationally intractable to fast forward every single point in the set and simulate all of those points. Like that's not in play right now because that's something that is like the forward propagation idea, which means that if I had 10,000 processors, I could do it in real time if I sampled it to 10,000 points. And so we're looking to find some techniques that might look at the overall set itself and its propagation, which might be handled in some way by the bounds of that set or the dynamics of the evolution of the bounds based on what we would know. And that's why the set dynamics themselves are important. And so I think we need some new computational tools to be able to do this. But if we can find those tools, then the payoff is going to be a return from the result that would say, I know that you can fit, for example, within this gap, and this is a range of inputs that allows you to do that. So you don't get back a specific trajectory to follow that might be right on the edge, but you get a range that you could follow from which you could select a trajectory to follow. So the opportunities could be really great, but I think the field is wide open for what the computational solutions might be.
Thank you very much.
So I think there's some tools from like finite time reachability analysis that could help. I know you had some reachability in your talk as well too, but I think there's tools where you can still have initial sets of states and you have disturbances at each step as well that could propagate. They try to propagate sets through differential equations. Doing it in real time is a little bit difficult, especially if the dynamics are nonlinear, but the tools exist.
Mm-hmm.
So Stanley, if you could point to some of the tools in the chat, that would be very helpful, and we would like to have a follow-up on that.
Sure. Yeah.
So, is there any more question? We are actually in the break time before the next session starts. So, if there is no more question, I thank Jonathan again, and Ricardo, you are chairing the next session. Yeah.
Yes.
Yeah, very good. So yeah, be back in 10 minutes. Yeah. Have a nice coffee break or lunch break for 10 minutes.
Lunch time for us.
Never too late for coffee.
Too late. Oh yeah, it's too late for coffee. You don't sleep anymore. Yeah. For me, it's the other way around. If I have coffee at night, it makes me to go sleep even faster. So then I don't drink coffee afternoon because I go to sleep sooner. So I have tea in the afternoon.
You have an Italian kind of DNA, because I remember the times I was in Italy, people would have espresso after dinner and they would even go to bed. I never tried that, but it seems like it's possible.
Yeah, an example, it's me.
It is really tough to beat some espresso with chocolate, though, for an after dinner snack.
Yeah, especially in Italy, right?
An espresso and a tiramisu.
Ah, that's exactly what I was thinking of.
So I guess we are almost at the half point, right? We probably won't talk over half point on sessions. So how's everybody doing? And